everyone, in this video we're going to discuss completely about asymptotic notations. It's a very important topic. So before you watch this video, first I request you to please watch the previous video. So let's get started. First of all, before you look at what are asymptotic notations, why do we need these asymptotic notations? The answer is very simple. See, if you have to compare two algorithms we've seen in the last video, those functions. If you have to compare which function is better, in order to know that, we use something called as asymptotic notations. Now, there are three types of asymptotic notations: big O notation, big omega notation, and theta notation. Like, regarding this big O notation, we have seen this in our previous video. Like, whatever I've told in the previous video, I've just brushed it up like that. But in this video, we're going to talk everything related to mathematics, like everything in terms of mathematics. We're not going to talk everything in terms of industrial thing. I will also tell you what this talking in terms of mathematics and talking in terms of industrial is also. I'll tell you what the difference between both of that is. Now, first of all, let's look at the big O notation, which we are very much familiar with. This is the definition. Okay, the function f of n equals big O of g of n if and only if there exists positive constant c and n not such that f of n is less than or equal to c into g of n, where n is greater than n naught. I know you didn't even understand a single thing here. Now, first thing I would like to say is big O notation is an upper bound notation. I'll also tell you what upper bound notation is. Just wait, we'll slowly discuss each and everything in detail. Okay, so this is the definition, which doesn't make any sense right now, but slowly it will start making some sense. Assume a function f of n equal to 3n plus 10. You know, right, last time we have seen this algorithm thing. Okay, so you have a function 3n plus 10. Now, you should write this in such a way that it satisfies the condition. See, now what I'm telling you to do is, you are supposed to write something in this particular blank such that that particular value is greater than or equal to this particular function. Okay, so whatever you write in this particular blank should be greater than or equal to this particular thing. Let's say I wrote 15n over there. Now let's verify with some values. If I put n equal to 1 on both sides, what would the value be? You would have 13 on left hand side and you will have 15 on the right hand side. Now 15 is greater than 13, so this satisfies the condition. Let's say you put the value n equals 2. What would you have here? If you put 2, it will be 16 on the left hand side and it would be 30 on the right hand side. So 30 is greater than 16, so this satisfies the condition. You might get another doubt. What if I put the negative value then? If you put, that's why here you could see in the definition where n is greater than or equal to n naught. So here the condition is given. It should be a positive value. The value of n should be positive. That is what is mentioned in the definition at last. So here if I put 15n, where this particular thing is f of n and this is the value of c, this 15 is c and this n is g of n. Okay, so I could say that f of n is big O of n. We have seen all regarding these rules, how we write all these things. We have seen in the last video. You please check that out. I'm telling this again and again. Okay, so here f of n is big O of n. So this is fine. Okay, these are all the time complexities which you will be looking at in your entire lifetime. It's like this. You'll have big O of 1, big O of log n, big O of under root n, big O of n, big O of n log n. You'll be only seeing these time complexities, or you could also say, you could see big O of n into m, all such time complexities you will be seeing. You will see these time complexities or the multiple of these numbers. Apart from these time complexities, you're not going to see anything. Okay, now in this time complexities, the value we got is big O of n. Previously we got the value as big O of n. Whatever is present after n is considered as upper bound. I've told you that big O notation is an upper bound notation, right? I've told you that before itself. So whatever is present after this particular value n is upper bound. Here, the function which we have taken before, the 3n plus 10, that belongs to the n class, and whatever is present after the n class, we refer to that as upper bound. So whatever functions are present to the left hand side of n, we call them as lower bound, and we call this particular n value as average bound. Now if you look at our particular example, if you look at this one, here big O of n is the value we got. So big O of n is true, and big O of n square is true, big O of 2 to the power n is true. This is the meaning of upper bound. Whatever value is present after n is true. So big O of n is true, n log n is true, n square is true, n cube is true. All these values are true. But if you look at, if I want to say that it is big O of root n or big O of log n, then that is false, because that belongs to the lower bound. Alright. So I think till now it is clear. The next thing that might strike your mind is, you're telling that big O of n, n log n, n square, n cube, all these values are true for the function 3n plus n. That's what I'm telling, right? So if I write the program in big O of n square and big O of 2 to the power n and so on, is that equal to big O of n? Now this is the doubt that might come. Like, is big O of n and big O of 2 to the power n equal? Or is it fine if I write the program in big O of 2 to the power n? The answer is, if you write the program in big O of 2 to the power n, it is correct, but it is not accepted. See, the first statement I've given is, I'll be talking in terms of mathematics and not industrial. See, I'll explain you here. If you look at this thing mathematically, big O of n is correct, big O of n log n is correct, n square, n cube, 2 to the power n, 3 to the power n, all these values are correct. But they're not valid in real life. In real life, the program should be in big O of n. In this case, it should, big O of n is the ideal case here. Big O of n log n, n square, all these things are not ideal at all. You might say, why? Why are they not ideal? See, it is very simple. For example, a guy wrote a program in big O of n and another guy wrote the program in big O of 2 to the power n. His program takes a lot of time to run and your program executes in a very fast time. Both of your programs are correct. He is also right, you are also right. But his program is a very slow program and your program is a very efficient one. So you will be selected, or you will be taken into consideration if you look at the real life scenario. So that is what mathematically and in terms of industry means. Here, whatever I'm going to talk about, this is all mathematical, this is all theoretical, just for understanding the concept. So this is all about it. You might get one more question. You immediately said that here the value is 15 and you just kept the value 15, and how do you know the answer? Did you read the answer somewhere before, or how did you get to know that 15 is the answer? See, the answer for this question is very simple. You can put any value which satisfies this condition. Now I can also put the value as 5n square, I can also put the value as 10n. Unless and until it satisfies the condition, I can put that particular value. The condition is, the value you put here should be greater than or equal to this particular function or this particular algorithm. So this is all about big O notation. Big O notation is the upper bound notation. I think I need to again brush up everything because some people might get confused. So big O notation is very simple. The value you put in this particular blank. Now don't assume like blank, I'm telling in the sense it is just for representation. whatever value that comes here should be greater than or equal to this particular function. You'll have one function and that value which you get should be greater than or equal to this particular value. You can put any value, but there is one condition here. You can put any value, but it shouldn't have two terms like this. The value you put here shouldn't be like 3n plus 20 or something like that. It should be only a single term like 15n or 15n square, 15n cube. You put anything. So this is the condition, and here whatever values you have upper bound, all of those values are true mathematically, but not industrially. So this is a very theoretical concept. Understand it only in basis of, like, understand it in terms of a concept, but this is not industrial. Okay, we'll discuss. There are more videos. I'll post more videos, and in that we'll understand everything clearly, so you don't worry. Okay. All right. Now, the big omega notation is a lower bound notation. So first of all, let me read the definition very quickly. The function f of n equals omega of g of n if and only if there exists positive constant c and n naught such that f of n is greater than or equal to c into g of n, where n is greater than n naught. In the previous case, it was less than or equal to, like, c of n, c into g of n is greater. Here the c into g of n, the value that should be lesser. Let's look at an example. I don't know why I'm stammering like this. Okay, let's look at an example here. Here we have f of n equals 3n plus 10. Now this 3n plus 10 should be greater than or equal to the blank value. Here I've taken the blank value as 2n, which satisfies the condition. Let me put the values of n for your happiness or something. See, if we put the value of n as 1, on the left hand side it will be 13, and on the right hand side it is gonna be 2, which satisfies the condition. 13 is greater than 2, so this value is valid here. Now again, you can put any value of your own. 2n is not the only correct answer or something of that sort. You can put any value which satisfies this particular condition. Now here the 2n value has satisfied this condition. Now we can say that f of n is omega of n. In the previous case we have said f of n is big O of n. Here we are saying it is omega of n. Now if we look at this particular time complexity, here we have the n, and whatever the values which are present below n, to the left, below in the sense to the left hand side of n, are all lower bound. So the speciality of this omega is it is true for all the lower bound values. Now big O of n is true, big O of root n, big O of log n, big O of 1, all these values are true. Now if you say, is big O, no, I'm so sorry, it's not big O, it's just coming out of habit. For omega of n, omega of root n, omega of log n, omega of 1, all these values of omega, it is true. Now if I say, is omega of n squared true, then that is not true. That is what I've represented there. Now let's look at the theta notation. Theta notation is no different. It is also very similar to this, but a slight change. Here you just read the definition. I'm really bored of reading this definition. Here the only difference is it is true only for this particular condition. C1 into g of n should be less than or equal to f of n, should be less than or equal to C2 into g of n. Here, due to this color, I think you couldn't identify that particular thing. So just look at this clearly. C1 into g of n should be less than or equal to f of n, should be less than or equal to C2 into g of n. Now what is the C1 and C2? You might be thinking, let's take this only algorithm which we are using for the 3 examples, which is 3n plus 10 here. Now this 3n plus 10 should be written in such a way that it satisfies this particular condition. Now here, this is C1, this is g of n, and this is f of n, and this is the C2, and this is g of n. Let's put the value of 1 over here. Let's put the value of n as 1. So here it will be 2, and here it will be 13, and here it will be 6. Now this satisfies the condition. Now I can say that f of n is equal to theta of n. Now, when it comes to theta, can I say that upper bound is true or lower bound is true? Which bound is true? If I say f of n of theta, f of n of theta of n and f of n of the function of like theta of n and theta of n square, theta of n log n, all the which of these values are true? If I like compare between them, these both values are wrong. You cannot go lower bound nor you can go upper bound. If the value of f of n is theta n, it is theta n itself. You cannot say it as theta of n squared, you cannot say it is theta of 1. You cannot go lower bound nor upper bound. It should be, if the value of f of n is theta of n, it is theta of n and nothing else. Now let me just brush up everything. Let me just give a summary of everything. I think by now you might have understood everything clearly, but still, if you are left with some sort of doubts that regarding this, I'll just give a summary. If you really understood this video, then fine. You don't watch from this part, but watch from this part. Come on. If you listen to this once again, it'll be in your mind. It'll be fixed in your mind. You need not, think of this again. Yes. For big O of n, it is, for example, if you have this particular function, the value you write on the right hand side should be greater than or equal to this one. So that is what big O of n is. And this is, in big O of n, we care about the upper bound. See, if you got the value of if you got the answer as big O of n square is true, n cube is true, n log n is true, everything is true. Everything which is present in the upper bound is true, everything which is present in the lower bound is not true. These values are all true, and that is not true. And big omega notation, f of n should be greater here. This particular value should be greater, and whatever the value you write here, this should satisfy this condition. You should always make sure this value is greater, and this is this omega notation is true for all the lower bound, and all these upper bound values will be false. All the lower bound values are true. Okay, that is what I've represented there. Now we'll look at the theta notation. In theta notation, this particular thing should be satisfied. C1 into g of n should be less than or equal to f of n, should be less than or equal to C2 into g of n. If you have this particular function, you should write values in such a way that it satisfies this particular condition. All right. And regarding this theta notation, there is no upper bound, there is no lower bound, there is only one value, that is that particular value itself. If it is theta of n, it is theta of n only. If it is theta of n square, it is theta of n square only. All right. Now I want you to tell one more thing, which is, now if I've given this particular algorithm here, and for this value we've got this theta of n, and we've got this value. Okay, now if you look at different algorithms, we get different values. So just don't stick to like theta of n is the only value, or big O of n is the only value, like that. You don't stick in that way. Okay, it is like it keeps on differing for different algorithms, but I just made you understand the concept with this particular example, so these values are all coming. I think you know this thing, but still I'm giving a clarity. Okay, so, and there is one more thing I need to discuss, which is the best among this big O, big omega, and big theta. The answer is big theta notation. You might say, why big theta, why not big O and big omega? See, it is like this. In big theta, you're not caring about the upper bound and you're not caring about the lower bound. If you have the answer as theta of n, it is theta of n itself. So here, this is big theta, you also call it as average case. So, I'm sorry, average bound. You call the big theta as average bound. So, whatever value you get, that is almost a perfect value. But if you cannot mention it in terms of big theta, you can mention it in terms of big O or big omega. In big O and big omega, we refer to the upper bounds, and we like the value of upper bounds is can be true, and in big theta, in big omega, the value of lower bounds can be true. But in terms of big theta, we have only one value and no other value can be true. So this is a bit exact, or you could call it some sort of perfect thing. So if you're trying to write something, write it in terms of big theta, that would be great. If you couldn't write it in terms of big theta, then write it in terms of big O or big omega. So I think this particular thing is also clear. So now you might be thinking, like, we have three you might be thinking we have three asymptotic notations, and which one to use. You might have thought about this, and that answer was also clear. Now it is like this: you have this algorithm and some other person wrote some other algorithm. In order to compare which algorithm is the best, this particular three things, big O, big theta, and big omega, these three things are gonna help you in measuring which algorithm is the best. Whether his algorithm is the best or your algorithm is the best, how are you gonna measure it? You're gonna measure it using these three things, and these are the conditions for each of the thing. I hope this is clear.
Hope this video is very much clear. If this is not clear, then please do rewind the whole video and watch it once again. Thank you so much for watching this video. Please do like, share and subscribe to my channel so that it gives me a lot of motivation to make more and more videos. Until then, we'll meet in the next video.